Hello and welcome to today's webcast brought to you by Waterworld and Headworks Bio. My name is James Laughlin. I'm editor of Waterworld magazine and will serve as moderator. Today's event, Innovative Applications of MBBR and IFAS for Upgrades, Retrofits, and New Builds Around the World, will be presented by Siva Angapan, Director of Process Engineering and Technology at Headworks Bio, and Afnan Din, Vice President and Process Manager for MENA Headworks Bio. Headworks Bio is one of the oldest independent MBBR IFAS technology providers in the biological sector. It has approximately 15 years of experience in municipal, industrial, and marine applications. The company is based in Houston, Texas, with offices around the world, including Canada, India, and the Middle East. Siva Angpan will be first up speaking today. He has more than 20 years of experience in environmental engineering, including 12 years of experience in designing moving bed biofilm reactor systems and integrated fixed-film activated sludge systems. Prior to joining Headworks Bio and his predecessor, Hydroxyl Systems, Siva worked with major consulting companies in the USA, including Rust Raytheon Engineering and Jacobs Engineering. Also speaking is Afnan Din, who joined Headworks Bio, Inc. with over 10 years of experience in the water industry in both Europe and the Middle East. Prior to joining Headworks, Afnan worked for two of the largest and well-respected engineering consultants in the industry. He began his career in the United Kingdom working with NWH as a process engineer and subsequently joined Halcro in Dubai, where he was primarily responsible for developing Halcro process capability and its process team in the region. Today's presentation is both live and interactive, so you can ask questions at any time by clicking on the Ask a Question button in the presentation window. We will respond to questions at the end of the presentation. If you are running pop-up blocking software, you will need to disable it to view this webcast. In addition, it is recommended that you close down all other applications for better performance. For your convenience, this presentation will be available on demand within 24 hours of this live event. A reminder email message will be sent to all registrants with a link to the archive. It will also be accessible from the homepage at waterworld.com. This webcast includes an option to earn a certificate of attendance. To earn the certificate, you must remain online until the end of the presentation. In addition to supporting audiences on the Internet using Adobe Flash and Microsoft Windows Media, Pinwell now offers webcast viewing via Apple tablets and phones running iOS 4.2 Plus. You will now have seamless access to both live and on-demand webcast presentations on your iPad and iPhone. Now it gives me great pleasure to introduce Siva Angapan. Take it away, Siva.
Thank you, James. Welcome to our webcast, Innovative Applications for MBBR and IFAS. My name is Siva Angapan. I'm talking to you from Victoria, British Columbia in Canada. I understand a lot of people dialing in from different countries around the world with different time zones. So good morning, good afternoon, and good evening. Today's presentation has two parts. The first part will be describing the technology and how it compares to other technologies and how it can be applied. The second part, we will go through certain number of case studies, both in North America and internationally. Biological treatment technologies for wastewater treatment can be classified into two parts: suspended growth, which includes activated sludge, and attached growth, which includes fixed film technologies. In activated sludge, we have a number of variations, including SBR and MBR, those kind of things. In fixed film or attached growth technologies, we have trickling filter, rope media, RBCs or rotating biological contactors, and MBBR. So most of these technologies can be combined, that is, attached growth and suspended growth can be combined to form a new technology called IFAS, which is Integrated Fixed-Film Activated Sludge. These are some of the examples for attached growth or fixed-film technologies. The top left, you see trickling filter, which is probably the oldest technology in the world. The top right, you see rotating biological contactors. The bottom two pictures are the MBBR, in which a suspended plastic carriers are put inside biological reactors and mixed very well to provide equal opportunity for the bugs and substrate to get in contact. So what is MBBR? It's moving bed biofilm reactors. There are a number of different technologies that use bed type of things, like fluidized bed. So this moving bed, the entire bed is moving around continuously and vigorously moving around. Typically, the carriers used or the plastic media used has a specific gravity of less than 1, so it's easy to mix within the reactor. There's a number of documented research and case studies and presentation publications regarding moving bed biofilm technology. How does a biofilm work? The biofilm is formed on the surface of the plastic media, where hundreds of layers of biofilm are formed during acclimatization, and the biofilm is basically a boundary layer between the surface and the substrate. The substrate contains all the contaminants to be oxidized, and the biofilm contains all the bacteria. So the substrates continuously mixed around, and all the contaminants like BOD, COD, different contaminants like organic compounds, they get into the biofilm, and oxygen also disperses into the biofilm, and on the surface of the biofilm, bacteria oxidizes the contaminants, and the products of the oxidation are sent back to the substrate and goes out of the reactor. This is the general principle of the biofilm. The key components of a biofilm reactor are the aeration grid and the retention screens and activated sludge. Active cell media, which is our specific brand media. Aeration grid provides the air required for oxidation as well as for mixing. The retention screens keep the plastic media inside the reactor and lets only the water out, the treated water out. And the media is where the biofilm resides. In more complicated projects, you will have a requirement for anoxic reactor, where nitrates are removed by anoxic bacteria to form nitrogen gas. In certain other complications, you will have a retention screens that can be retracted for easy cleaning and put it back in service. How does a biofilm look like? For the BOD bacteria, the biofilm looks either greenish or grayish. In the nitrifying bacteria, the biofilm is usually red. It takes a few weeks for the biofilm to form during an acclimation process. After that, the biofilm is self-sustaining and automatically adjusts to the load. So what is the difference between IFAS and MBBR? MBBR is a once-through process. There is no recycle of the waste sludge or recycled sludge. In IFAS, the activated sludge or the MLSS is recycled back to the front of the reactor. So you'll have two levels of biological activity. One is in the suspended growth with the MLSS, and the other in the attached growth on the biofilm. So why would you select MBBR over IFAS or IFAS over MBBR? The key parameters are how much space you have, and is it a new site or is it already an existing site? So if you already have an activated sludge plant with the clarifiers and all the supporting works, it makes sense to go for the IFAS process. So all you need to do is add media and add additional air if required on retention screens. So by doing that, you can expand the capacity of the system within the same tanks or same footprint. You can also meet additional requirements for nitrogen removal or phosphorus removal. In the MBBR, the process is very simple to operate because it's a 1-2 process. There is no recycle. So in that case, you don't need a skilled operators. There are a number of MBBR plants we have which need only 15 minutes of operator attention per day. Whereas IFAS, there is a need to maintain the MLSS at a constant level. So if we have skilled operators, it makes sense to go for IFAS. And if you don't want a full-time operator, then it makes sense to go for MBBR. So this is a conceptual concept of modifying an existing conventional activated sludge system into an IFAS. So the blue square on the left is the existing aeration tank at an activated sludge plant. If you want to expand the process with the activated sludge, you will have to add more tankage for meeting new requirements or expanding the flow capacity. Whereas with IFAS, you can keep the same tank and add the media into the same tank and meet the new requirements as well as increase the flow capacity within the same volume. This is more of a concrete example of how to do it. Let's say you have a 10,000 cubic meters per day water flow and 200 cubic meters of tankage, and that's meeting only BOD requirements. So we can convert that into IFAS by dividing the existing tank into 2 tanks, one for BOD and the other for nitrification. So we're adding new requirements for ammonia, nitrogen. The flow can be increased by 50% to 15 MLD or 15,000 cubic meters per day. By doing this, we have actually basically met the new requirements for ammonia as well as increase the flow by 50%. This is one of the most common implementation of the IFAS process. So how do we design MBBR or IFAS processes? It's just like any other biological technology, you need to consider temperatures, dissolved oxygen, and nutrients. In biofilms, hydraulic retention time is much less than activated sludge plants for a simple BOD or nitrification process. Typically, it's a half to quarter of what's required for activated sludge plants. More importantly, in the primary design factor that's used for designing MBBR and IFAS is the loading rate. That is grams per day of BOD or ammonia or nitrogen per square meter of the surface area of the media. So what you do is you take the total load in grams per day and divide by the total amount of surface area of all the carriers in the reactor. That's the design factor we use. So if you are designing a high rate system, you could use as much as 15 to 25 grams per square meter per day for BOD. Or if you are trying to meet very low limits and you're trying to do it in a single reactor, that should be a low loading rate situation. For nitrogen, biofilms can easily handle up to 1 grams per square meter per day. So in the next part, Afna and Din will go over the MBBR and IFAS technology in more detail.
Hello everyone, thanks Eva. I'll talk to you a bit about, on this slide, the differences from conventional treatment methods when you compare MBBR. What I've done is I've split the technologies into 4, and we're looking at 2 attached growth processes and 2 suspended growth processes. MBBR and RBCs are 2 common attached growth processes, and activated sludge and SBR are 2 suspended growth processes. The differences in the technologies really stem from the fact that one set is an attached growth process and one set is a suspended growth process. So if we compare MBBR, for example, with RBCs, one of the key differences in the 2 technologies is the footprint. MBBR is a super small footprint compared to an RBC. The second key difference is in the operation and maintenance of an MBBR. Compared to an RBC, an MBBR has absolute low mechanical equipment. There's no maintenance required of the media or the retention sieves. The only maintenance is required would be with the diffusers, if any. Whereas in RBCs, there are motors, there are rotating contactors, so there's far more maintenance required with an RBC. Now, in terms of activated sludge and SBR, both of those are a suspended growth process. Again, compared with MBBR, and MBBR offers the smallest footprint of the three. The key difference between an activated sludge and an MBBR would be in the operation and the control. An activated sludge requires you to control your mixed liquor, requires you to have a sludge age, whereas an MBBR process is an attached growth process. In terms of nutrient removal, an MBBR process is far more stable than an activated sludge process. Now, when you compare a sequencing batch reactor and SBR with an MBBR, again, one of the key differences would be the area, the total footprint, the space requirements. So an MBBR is far more smaller. And the second would be, again, similar to the activated sludge, would be the operation and the control of an SBR compared with an MBBR. Moving on to comparing two most popular technologies these days, and I'm looking at the membrane bioreactor and the MBBR. And what we see here is that one of the key differences in the two technologies is the capital investment. Although membranes over the years have become far more cost competitive, membranes are still very high in capital cost compared with the media for an MBBR. The footprint, both plants offer you small footprints, super tight footprints. An MBR can operate with a mixed liquor of up to 12, 15,000, if not higher. And an MBBR operates with an equivalent mixed liquor, because it's an attached growth process, of about 8 to 10,000. In terms of power requirements, as we know, blowers consume the most power on a wastewater treatment plant. And if you look at the number of blowers or the amount of power that's required on a membrane bioreactor compared with a moving bed biofilm reactor, well, both processes require blowers for aeration to provide oxygen for oxidation and removal of organics, but there's far more power required in MBR because you have recirculation pumps, and most importantly, depending on the type of membranes you go for, you have air scouring blowers, which is basically to keep prevent your membranes from fouling. Neither of those are required for MBBR. In terms of pre-treatment, we all understand one of the key success of an MBR is upstream pre-treatment. And if you want your membranes to perform well, then you need to prevent them from fouling or minimize the rate of fouling. So pre-treatment is a key criteria in membrane selection, and your pre-treatment in terms of your fine screens have to be typically less than 1 millimeter, although some suppliers say 2 to 3 millimeters will do. Whereas for an MBBR, we recommend 4 mm, but we can withstand up to 6 mm of pre-treatment in terms of screening. In terms of chemical usage, membranes typically have regular usage of chemicals to prevent the membrane from fouling, whereas with the media inside the MBBR tank, there is no requirements for chemical dosing to keep the media clean. In terms of operational difficulty, having operated both plants, I can personally say that an MBBR is far easier to operate because there's nothing much there to operate. It's a self-regulating process, whereas for a membrane plant, for sure there are far more controls and operational know-how required, especially with periodic cleaning of the membrane. So you have to take the cassettes out or the membranes out for periodic cleaning. So we looked at MBBR earlier, and Siva touched on the difference between IFAS and MBBR. So just to sort of recap the difference in IFAS and MBBR, the key difference is that one is a straight-through process and one has a return loop. The return loop of the activated sludge from the clarifier provides you with the suspended growth. So that's the key difference between IFAS and MBBR. In IFAS, we say Integrated Fixed-Film Activated Sludge, so it contains both suspended and fixed film. The advantages of IFAS and MBBR. Why would you consider an IFAS MBBR? Well, one of the key advantages is that it's a self-regulating process. So So the biomass is self-regulating, so there's no requirement to actually control your mixed liquor. Because it's an attached growth process, the thickness of the biofilm attached to the media is either thick or thin, depending on your influent load. So that's a natural process. One of the key benefits is that it offers a flexible design to allow future upgrades. So if you have an existing MBBR or IFAS reactor, and as we all know, plants after a period of time need to be upgraded, populations go up, incoming flow increases, effluent standards get tighter. So it's very easy in terms of flexibility to be able to retrofit these plants, because by playing around with the fill fractions of the media allows you to create a higher specific surface area for the growth of biofilm. In terms of operational adjustments, like I've explained, an MBBR is a fairly simple process to operate, especially because the control is not necessarily required as much as you would find on other technologies. It's stable under large load variations. Typically, if you have a labour camp, you have a hotel resort, which is likely to have seasonal variations or have peaks and low loads at certain times of the day due to the usage, then a biofilm process operates typically a lot better because of the self-regulating biomass nature. And as we understand, it's a very small footprint. It's very compact because of the media allows you to have a higher specific surface area. Now, looking at the different types of applications that where you could use MBBR. Well, the first application is simple. It's BOD, COD removal. So an MBBR is a biological process. It removes all and various types of organics. The second type of application could potentially be as a post-nitrifying reactor. So there are various flexibilities with MBBR as how you apply it. So, for example, if you have an existing lagoon, which is only for carbonaceous removal, and you like to nitrify the effluent, then you could add an MBBR as a post-nitrifying step downstream of the lagoon. And lastly, you could simply have a process where you could denitrify, BOD removal, followed by nitrification and post-denitrification, depending on your nitrogen limits. If you notice on the denitrification drawing, it's very similar to an MLE process. It's like an activated sludge process in terms of configuration, but with added media inside the reactor. So you still have an internal recycle, you still have a return activated sludge, and if need be, you'll have a carbon source. What we're seeing on this slide is an example of an IFAS application. And what we're seeing is that if we have an existing plant, which is for carbonaceous removal only, and it has BOD and TSS removal, so the effluent limits are less than 30 milligrams per litre. Now, if we have an existing activated sludge plant operating like this, which needs to be upgraded or retrofitted to give you a better performance, let's say less than 1 ammonia, then what we can do is retrofit the existing activated sludge plant into an IFAS and improve the effluent quality all within the same space. So there are various variations how we could do this without increasing the space requirements. So for example, in the first example, we could convert the existing plant from a carbonaceous removal only to a nitrification plant, giving you ammonia less than 1 within that same space. If you wanted to denitrify, depending on the limits of total nitrogen that you would want from your effluent quality, you could split that reactor into 3 steps of pre-denit, BOD reduction and nitrification, or you could have 4 steps depending on your total nitrogen limit of pre-denitrification, BOD reduction, nitrification and post-denitrification. So again, what we're really trying to show here is that for existing plants, an IFAS application is ideal if you want to increase your capacity and improve the performance. And just so you know, this actual example is working out in the UAE for the last 5 years. So the existing plant was actually retrofitted and upgraded to a nitrifying only plant, and the capacity was increased by 30%. So for example, if you have an existing activated sludge plant and you would like to retrofit this for nutrient removal, this is a very common requirement these days. Consents are getting tighter, environmental agencies are imposing tighter limits, and there are requirements for nutrient removal. So one way we could retrofit an existing plant into nutrient removal is similar to how I explained earlier. What we would do is we will create inside the aeration tank separate tanks of BOD reduction and nitrification by converting them to IFAS. By doing so, this allows an available volume for anaerobic treatment and pre-denitrification. So what this does is it allows for suspended growth sludge age such that you can tailor it for the maximum phosphorus removal. So you allow suspended growth in your BOD reactor, nitrifying reactor, and then you can create a volume for your anaerobic treatment. I'll pass you over to Siva, who will be talking to you a bit about our project in the United States.
Thank you, Afnan. So I'll be talking about, in really briefly, about our municipal project in Minnesota and an industrial project in Indiana. So Moorhead, Minnesota is in very cold weather. The temperature can reach, the wastewater temperature can reach less than 10 degrees most of the winter. And they have an existing Purox plant which is meeting BOD limits, which was meeting BOD limits, and they had a new requirement for MBBR, new requirement for ammonia. So we decided to install an MBBR for this particular project as a separate stage. What that means is this nitrification process is after the secondary clarifier. So initially they looked at the existing lagoons to nitrify the wastewater, but it's not going to work based on the temperature. So we installed the MBBR process for the nitrification. These are some data for the wastewater influent data. The flow is typically between 4 and 8 mgd. The temperature is highly variable depending on the season. So in winter, the temperature can reach 6 degrees centigrade. The pH is quite constant. So this graph shows you the influent and effluent ammonia nitrogen concentrations. Influent is typically 20 to 40 milligrams per liter, and effluent is less than 5 milligrams per liter. The x-axis on this graph is number of days in the year 2010. The plant was originally installed in 2001, so these are just data for the 2010. So the date 0 is January 1st and goes up to 365 days. As I mentioned previously, the primary design factor is the loading rate. So this graph shows the loading rate, ammonia nitrogen loading rate on the x-axis and ammonia nitrogen removal on the y-axis. The red line you see is the 100% removal line. So what that means is if you load the system, the MBBR system, at 1 grams per square meter per day, and if you remove close to 1 grams per square meter per day, that point will be on the red line. If you are removing less than 60%, for example, the data point will be far away from the line. So we sampled the wastewater at different points throughout the year, for different seasons. And this is how the data points look like. So the general conclusion is that if you have a high loading rate, the removal rate will drop. So this information can be used 2 different ways. You can design 2 reactors, the first being high loads and the second being low loads. So if you have a very stringent limit, you should either use low loading rates with a single reactor, or you can use two reactors, the first one being high load, second one being low load. The second case study is a small installation in Indiana. This particular plant recycles glycols used in aircraft de-icing. In North America, it's a standard practice to use glycols to de-ice aeroplanes in winter when there is a snowstorm or ice storm. So all those glycols are collected. This particular plant collects about 5 to 6 million gallons of glycols. And then it's throughout the winter, and then treat it throughout the year. So it's the wastewater comes in over 3 months, but the treatment system operates 365 days to treat the 3 months of wastewater production. So this particular plant, it is quite complicated because of the it's an industrial applications. There could be a lot of inhibitory substances. So we decided to do complete design based on testing rather than design a complete system and trying to operate it at that point. So we started with, we had a plan to do batch testing to get some preliminary design factors for a continuous flow testing, and then use that information for the full-scale design. The COD is 15,000 milligrams per liter, and the BOD is SIS 10,000 milligrams per liter, and they had a requirement to meet COD of less than 550 milligrams per liter, and phenol of less than 2 milligrams per liter. As you know, phenol is difficult to oxidize using biological oxidation, so that's an important consideration. So in the lab testing, we made a simple tube-type reactor, 14 liters in volume, and then put in the media inside and use the sparges to disperse air into the reactor, and nutrients were added. So batch testing is simple. You start with a batch of wastewater and see what happens to the concentrations of COD over time. So based on this testing, the COD over time drops from 12,000 down to less than 1,000 within about 100 hours, 100 to 150 hours. So that gives us a preliminary indication of how to size the next step, which is the continuous flow reactors. So using the similar type of reactors, we prepared a water, initially diluted sample, and then ramped it up later with the full strength wastewater. So we started with 2-to-1 dilution, and then acclimated the reactor over a few weeks. So once it's acclimated, you'll see that the COD influent is quite constant in the blue line, and after the acclimation, the COD effluent is also coming down after about a month or so. So at that point, the system has reached maybe 90% of the design capacity. So we also varied the hydraulic retention time after the system reached most of its capacity. So we reduced the flow rate, which will increase the hydraulic retention time, and then we wanted to see the effect of that. In this case, this is a single-stage reactor, so at this stage, the increase in hydraulic retention time did not make any difference to the treatment performance. That basically proved that our design factor is primarily surface area loading rate, not the hydraulic retention time, after a certain number of hydraulic retention time is reached. We also used a flocculation step to see that effect, if that COD can be reduced further. We saw that COD can be reduced further by 50% by using a chemical coagulation flocculation step. So based on this information, we designed a full-scale system, a single-stage reactor, and wanted to keep it simple, so that's why we went to a single stage, and they didn't have a lot of operators to run the system. So and we wanted to do it in a single stage and we wanted to have a lot of capacity for future expansion. So that's why we went with the carrier fill fraction of 30%, around 30%. This reactor is about 95,000 gallons per day, which is about 5-6 days of hydraulic retention time. So that gives you an ample amount of space for expansion. And we also included a flocculation step and a clarifier. We wanted to compare the results of the full scale compared to the full lab scale or pilot testing. So the full scale system, initially we started around 5 to 10,000 milligrams per liter, and on the long-term basis it averaged around 8 to 10,000 milligrams per liter. So the effluent after acclimation was always less than 500 milligrams per liter. And we wanted to see the effect on phenol. So based on those results, we always met 2 milligrams per liter limit for phenol. So this is where we compare the full-scale results versus pilot scale results. The squares, hollow squares are the lab scale results, and the blue squares, blue diamonds, are the full-scale results. As you can see, when you compare loading rate versus removal rate, the full scale is always better than the pilot scale. So that gives us enough confidence for other projects that a pilot system, the full-scale system, will always work better than pilot-scale systems. And it also gives us ideas about how to design the system based on these results. Now, Afnan will go over a few more projects, mainly in the Middle East and North Africa region.
Thanks, Eva. I'll quickly go through these and just to sort of give you an update on what we are working on in the Middle East and North Africa. A lot of these projects are actually in the execution phase. So they're either undergoing installation now, commissioning, or they're under construction. So one of the first projects that I'll have a look at, and it's a nice blend here, so you'll get to hear a bit about industrial treatment, a plant we've done for a university, and another retrofit and a plant in Egypt. So the first project is a textile factory, it's a denim factory in Bahrain, an interesting plant. It's actually an existing MBBR. So there were a few challenges here. One of the challenges was, firstly, the plant was not working, both in terms of treating the influent loads and in terms of the media. There was a problem with the media. It was sinking, so I'll explain why. So basically, the challenge here was that we had to increase capacity and we had to improve effluent quality. The effluent is discharged into the Bahrain harbour, and the client was incurring fines from the environmental agency. So what we did, we replaced the existing media in the 3 reactors. There were 3 MBBR reactors. So we replaced that with 30% active cell media, and we guaranteed an increase in plant capacity by 25%, and we guaranteed that we could meet an effluent requirement of less than 25 BOD and less than 150 COD. So if you look at the current performance of the plant, while it was treating 250 to 300 cubic meters per day, was that it was giving a BOD effluent of 250 milligrams per liter and a COD effluent of 1,000 milligrams per liter. And the limits were far less. So the limits was less than 50 for BOD and less than 250 for COD. So by retrofitting the 3 reactors with MBBR, we were able to increase the capacity by 30% to future design flow capacity of 400 to 450 cubic meters per day. The plant was commissioned earlier this year in January, and these pictures really just show you during the commissioning, the media entering the reactors. The picture on the bottom left of the screen shows during the seeding process, and the bottom right is with the MBBR in operation. A quick summary of the results. What you see is that initially when we were starting up the process and after the seeding phase, the flows were kept relatively low, roughly about 200 cubic meters per day. Roughly about 75 cubic meters per day to about 100. And throughout the whole process of the sampling, the outlet COD is below the desired effluent quality. Towards the end of January, so after about 4 or 5 weeks of feeding the plant with slightly lower flows than designed, we started to increase the flows by about first week of February. So the plant is now receiving its design flow between about 300 to 400 cubic meters per day. And the inlet COD concentration throughout the whole sampling period was very high, but the loads were obviously lower initially while we were seeding. And as you see, the effluent COD is always below 250. So as I explained earlier, this plant was a very unique plant for us in the sense that it was an MBBR and it was not working. The client obviously did not have much options on how to retrofit the plant because with an MBBR you already have a very small footprint. So he certainly could not turn his plant off. He could not build new reactors. There was a huge shortage of space. So what we had to do was we had to actually carry out a feasibility study and look at why the existing plant was not working. And as you see here, what you see on the right is media which was existing in the reactor, which is sinking to the bottom, and active cell media on the left, which is floating. The key difference here is that active cell media is virgin, and the existing media that was inside the tank previously was recycled plastic. So one of the key differences between recycled plastic and virgin media is the properties which are used in recycled plastic. Now, not only is the specific gravity greater than water, so basically it floats, but the specific gravity of active cell is between 0.92 and 0.96. Also, what happens here with the media is that the properties that the media is made of, it can potentially, after a few years of operation, have reactions with contaminants with inside the wastewater, which changes the density of the media. Reactions occur which causes the properties of the media to change. So over a period of time, that media starts to sink. And so even though you have aeration and you have air being provided, the media is not fully mixing inside the reactor, which means that your rate of reaction is lower, as well as you have a deterred effluent quality. One of the next projects that I'd like to sort of briefly touch on is what we're doing in Egypt. This again is a very unique application. This is a perfect example that membranes is not suitable for every solution. They had an existing membrane plant which was running for about 5 years. These are xenon membranes, hollow fiber, and after about 4 years in operations, the membranes absolutely fell apart. The fouling was immense. They were running these membranes at very high flux rates. They were cleaning them on a weekly basis using tons of chemicals. They were having to replace the membranes, take them out for cleaning. So it was an operator's nightmare. So what the client actually did here, he shut down the plant. For 2 years, the plant was shut down. Then the client looked into technologies which were available that could retrofit this existing reactor, this membrane reactor. The key thing the client wanted was a technology which was low in operation and maintenance. So it's idiot-proof. It can be easily operated. And secondly, a technology which could fit into the existing MBR reactor. And the only technology which was available that could be fit into the existing MBR reactor was an MBBR. So what we're doing here is we're removing the membranes, we're refurbishing the tank, we're converting it to an MBBR, and with a Headworks design clarifier to provide the complete solution. This plant actually looks at a 10,000 cubic meters per day plant for a university. It's based in Saudi Arabia, in the capital city. And one of the key drivers for a university, which was in the capital city, the oldest university in the country, was they wanted a plant, a wastewater treatment plant, which has low visual impact. And secondly, it gives minimal odors. And thirdly, again, it has to be easy in terms of operation and maintenance. One of the key challenges for the university is that a university would experience seasonal variations. Because of the students and because of the summer terms, there will be seasonal variations depending on how many students are on the campus. So one of the criteria was a technology that could handle such variations in load. And an MBBR really fits well into all those criteria because not only is it a small footprint, so in terms of a visual impact, it's very, very convenient. Secondly, in terms of operation and maintenance, we now understand MBBRs are very simple to operate. And thirdly, in terms of the total area, if you look at the total area, it really is 16 meters by 20 meters. This plant would provide the university with 10,000 cubic meters per day of reuse effluent quality. So this includes BOD removal, nitrification, and denitrification. And all the effluent will be reused for irrigation of the university playing fields. This plant's currently undergoing construction. It's planning to be commissioned probably in the next 6 to 10 weeks. One of the other projects, which is a very interesting project, is where we're retrofitting an existing plant which has a capacity of 20,000 cubic meters per day to 28,000 cubic meters per day. So again, it's retrofitting an existing activated sludge plant by increasing the capacity to 40% without any civil works and improving the effluent quality. The existing plant consists of 4 trains. The total flow is 20,000 cubic meters per day. We'll be increasing it to 28,000. What I must say here is actually when you increase capacities and when you increase flows, the limitation is not on the MBBR or IFAS side in terms of how much you can increase the capacity, but the limitations are normally on the hydraulics of the plant. So that's an important criteria. So that requires a lot of assessment on our part to go through the entire existing infrastructure, to look at where are the hydraulic limitations, to assess each process unit in the existing process stream, from interstage pumping stations to primary clarifiers to screens to all the interconnecting pipe work, to actually assess where's the hydraulic limitation. Because the limitation is never in the capacity to increase the plant in terms of adding media. I mean, we could increase the treatment capacity to 40,000 or 45, but the hydraulic limitations limit to what we can increase the capacity to. If we look at the influent quality here, typically the influent BOD is between 300 to 450, suspended solids is between 350 to 400, and ammonia between 35 to 45. We did actually carry out extensive sampling. We set up composite samplers to actually look at the influent wastewater data and analyze the influent wastewater to be able to accurately size out MBBR to know how much flow and load was coming into the plant. The effluent quality required was less than 10 BOD, less than 10 solids, and less than 5 ammonia. This is for restricted irrigation. So what you see here are the 4 aeration lanes. 2 are conventional rectangular aeration tanks, and 2 are typical carousel tanks, oxidation ditches. So what we're basically doing is that if you look at the drawings, look at the drawing here, is that we're creating a roughing reactor up front. So what this roughing reactor does, it's like we call it an MBBR roughing reactor, because what it really does, it knocks off 70% of your BOD load. So what we're doing is a higher rate reactor, we're loading it with media, and we're able to reduce your BOD. So we remove the bulk BOD, the easily biodegradable stuff, in the initial roughing reactor. What this then does is it allows the remaining volume of the existing activated sludge plant for nitrification. So sort of explaining to you how we did this, that you see here an example of a carousel tank. And what we did, we create an MBBR zone on the front end. So as the flows enter, we create a wall. Flows go over a weir into your MBBR reactor. The MBBR reactor is fitted with aeration grids and retention sieves, and then the flow, I'll show you on this on step 4, the flow would basically enter from an MBBR reactor on the outer wall, on the outer lane, into the internal lane. Now, it was a very complex, actually, solution, because we had to look at various different sorts of options on how we could implement the MBBR reactor. One of the key things that you have to consider is the approach velocities, because if you don't have the right approach velocities, what you could have is your media goes into one corner of the tank, so stacks up. So one of the things was that we had to consider that. We also had to consider which option would give us minimal civil construction inside the reactor. We didn't want to change the direction of the current flow pattern or build too many walls inside the reactor. So if you look at this, what we've really got is we've maintained the existing inlet. We've created a sort of reactor where the flows enter. The flows go over the weir into an MBBR, and from the MBBR flow into the central lane, and the flow then takes its original route right round the racetrack to the effluent weir. We did not move the effluent weir. And that shows you how it would look. For the rectangular tank, it's much easier because you have a clearer flow pattern. So what we do, we created a MBBR roughing reactor at the front end by creating a wall inside the reactor. We fit the whole aeration tank with coarse bubble aeration. The MBBR reactor is filled with aeration, diffusers and sieves. And the flows would enter from the left into the MBBR reactor and would pass through the retention sieves, which prevents the media from escaping, into your activated sludge reactor, activated sludge basin, the existing basin. So as a final overview, that's how the reactors would look. So in the carousel tanks, you see that the flow enters the MBBR reactor first, and then flows through the sieves right round. And in the aeration tanks, it's a single pass system. Now, one of the things that we had to look at, obviously when you're looking at a retrofit and an upgrade, is not just to look at the aeration tank, but to look at the whole process, as I explained earlier. Especially the hydraulics have to be looked at. So what we did, we also looked at the clarifier capacity, because sometimes there's a shortfall in clarifier capacity. So treating more flow, you've increased the biological capacity, naturally you're producing more solids. So you have to look at the clarifiers and assess the performance of the existing clarifiers. So we did that. The current system worked that there was one clarifier per each lane. And the clarifiers were designed, I mean, they were huge. So we assessed the clarifier capacity, and we looked at that, and we looked at what we could push through the clarifiers. And we felt that we could treat 28,000 cubic meters per day through the existing clarifiers. They were certainly oversized. Also to verify our results on this, we always carry out a biowind model to actually look at the implications of a real-life scenario of increasing the flows and increasing the loads to be able to guarantee the final effluent quality. So a lot of, in terms of the execution, is the easy part, but a lot of effort and time goes into the upfront designing of retrofits, where you have to really look at the existing infrastructure and see how that fits into your proposed retrofit. From a client's perspective, the client is super delighted. Why? Because he's maximizing the use of his existing assets. He's able to increase his capacity by 40%, which is great for him because he doesn't need new civil construction, and it saves time for planning permission, getting new land, availability of space. Minimal civil works, so that means that the lead time in executing such a process is much shorter. So he's not waiting for a year or a year and a half before he gets his 40% increased capacity. In this case, we were able to produce a consistent effluent of less than 10 BOD, 10 solids, and less than 5 ammonia. And in terms of reliability and how easy it is to operate, again, the MBBR reactor in itself is a very easy to operate system. And mainly, the client can now reuse 28,000 cubic meters per day for reuse, which is obviously a huge driver in a water scarce region, where it probably rains once in every 3 years. That brings me to the end of our presentation. Thank you very much, everyone.
Thank you, Siva and Afnan, for a very interesting presentation. We have a really huge number of questions here, and I'll try to hit the high points. Let's go with, how do you avoid media entering internal MLS recycle piping and BNR configurations? Siva?
Yeah, basically after the nitrification, you will have you need to de-aerate the wastewater using your de-aeration tank. But de-aeration tank, we don't have media. Nitrification tank, we have media. So we put a retention screen between those two sections. And that will prevent the media from going to the next tank. And then from de-aeration tank, you will have an internal recycle of nitrates back to the pre-anoxic reactor.
All right, thank you. Next question. You mentioned flow can be increased by 50% by adding media to existing aeration tanks. Is it possible to increase flow greater than 50%?
Yes, it's primarily dependent on the plant hydraulics, as Afnan mentioned. In theory, it can increase the flow by 200%, basically double or triple the flow within the same footprint for meeting the same requirements. If you are meeting BOD and by adding media, converting into IFAS, and then we can triple the flow, basically.
Okay. All right. Next question. Do you suggest air sparging directly beneath the screens to preclude the media from accumulating around the screens and restricted flow through the screens?
Yeah, that depends on the tank geometry and tank design. So if we have an existing tank, long, narrow tanks, it may be a factor. So you need air spargers under the retention screen. But if you are starting from scratch for a brand new MBBR or IFAS plant, we will design the tank to make the geometry so that the media will not bunch towards the retention screens.
All right. What would you say is the typical service life of an MBBR media, and what is an annual media loss rate?
Yeah, it's about 20 years. We don't have annual loss. We estimate it's 20 years. The technology itself pretty new in the sense that we have systems running for more than 12 to 15 years. We haven't seen any damaged media. So we still don't know the true life of the media, but we think it's at least 20 years.
All right, thank you. Next question. What percent nitrate recycle do you recommend, 100 to 150%?
It depends on your requirement for total nitrogen. And there are a lot of design considerations. You have to look at the recycle rate, the total nitrogen requirement. But basically, if you need to remove 50% of the nitrogen in nitrates form, then you need a recycle rate of 2. If you need 75%, you need 3. If you need more than 80%, you'll need a recycle rate of 4 or higher, but we don't recommend that high. If you have a limit of that requires you to remove more than 80-90% of the nitrogen, so you're better off removing portion of it in the pre-anoxic and the remaining in the post-anoxic zone after the clarifiers and everything.
What is the startup period for a typical MBBR system?
That depends on the wastewater. For a typical domestic sewage type wastewater, it's probably 1 or 2 weeks. In the industrial step situations, so there are so many other complications like bioinhibitory compounds, refractory compounds, and then you have conductivity, TDS, all those issues come. So typically it's minimum of 2 weeks. It could be as high as 8-10 weeks for a really complicated water with a TDS of like 5,000 or higher. So it's a normal situation. It's a couple of weeks.
I'd just like to add that the startup is also severely affected by the temperatures. So depending on the temperature and the climate where you're actually doing the startup, hotter climates naturally happens a lot sooner than the winter places.
All right. Next question. What DO level is recommended in the IFAS reactors to achieve nitrification?
I will go, typically, it depends on if you have only one stage you're probably going to target DO of 5. If you have a choice of 2-stage nitrification, then you will go with 3.5 for the first and 5 for the second. So all you're trying to do is save aeration cost, but there is a minimum requirement of around 4 for nitrification.
All right. Perhaps this one for Afnan. Are there any limitations on the width to length ratio of the IFAS reactors?
Not really, because it's a complete mixed system. So there's no requirement. It's not a plug flow system where you have a minimum of length to width ratio. So it really depends on the space available, on the geometry of the tank. But there's no, if it's a new build, there's no restriction on the length to width ratio.
All right. Does active cell media ever need to be serviced for solids removal, for example, in the event of COD overloads?
No, it's a self-regulating process. What that means is when the biofilm gets thick or old, it automatically dislodges from the carrier and goes out. So we will size the amount of media based on the loading. So we will make sure that there won't be an overload. But in case of accidental overload, the biofilm automatically dislodges itself and goes out into the next stage of solid separation.
All right. Kind of a related question. Do the active cell media shapes vary by application?
The shapes, not much, but the amount of surface area will depend on the application. If you have a really high load situation, then it's better to design with the media of lower surface area with the bigger openings so that you don't get plugging on inside the surface area of the media.
All right. How does MBBR compare with MBR for a given load and TN discharge target in terms of the required bioreactor anoxic and aeration tanks volume?
Shall I take this one?
Yeah.
Yeah, I mean, it really depends on what sort of total nitrogen limits you're trying to achieve. Now, from a membrane bioreactor, in the sense you've still got a very large aeration tank. So the aeration tank in an MBR is far larger than a total nitrogen system with an MBBR. So it really would depend on the total nitrogen limit. But if we take a less than a 10 milligrams per liter limit, now if you're comparing MBBR and a clarifier compared with an MBR, then for sure an MBR would have a smaller capacity. But let's not forget, a membrane bioreactor also includes the clarifier step. So the total volume or total area required by an MBR for a total nitrogen removal plant would be less than an MBBR, but it's about 10 to 15%. You know, it really would depend on the flows. So if I could get an idea of the flows from the person who has this project, but in the end, yeah, the difference is to about 10 to 15%, I would say.
Okay. Here's a question. We have an industrial process where we are considering a combination of MBBR with MBR. Has that been done before?
We haven't done anything like that. There are two different technologies. If you have a choice, you would go with one of the technologies. I don't know why you would want to combine two technologies unless one is already existing. You want to reconfigure it. But in terms of operator attention, we don't want to make them learn more technologies than necessary. There could be other complications, but we haven't done anything like that.
For Siva, could you explain again why you would have two plants when dealing with high loading rates when you discussed the Moorhead MN plant, Minnesota plant?
No, that's just a theoretical situation. We have only one reactor, but depending on the situation, we could have two stages in series. That will have some savings in terms of kinetics. So if we have a higher loading in the first reactor and lower loading the second reactor, there will be savings in energy because the first reactor will need less DO the first reactor will need less DO, so that will have some savings. And the kinetics can be improved too. Since our kinetics are based on CSTR, which is continuous flow type reactor, so we have to make sure that if there is any energy savings in terms of if you have large flows, that could be done. But in most situations, you probably go with one-stage nitrification.
All right. Is there a minimum screen submergence below the reactor liquid surface in one of these systems?
So minimum, usually it's right at the surface, so there is no requirement to have it submerged, because it's all our MBBR IFAS reactors are typically gravity flow, so we will leave it right at the surface of the water.
All right. Are the pinpoint flocks from an MBBR process more difficult to settle in a clarifier?
Yes. So if you have an MBBR process, the DAF is the better solid separation for removing solids. But if you have an IFAS process, clarifier will work very well.
And it obviously all depends on the sort of solids limit that you're trying to get. I mean, some MBBRs afterwards they do have some flocculation, coagulation, so it really depends on the effluent solids limit that you're trying to achieve.
All right. At one point during the presentation, you had an ammonia loading graph example, and why did temperature not play any effect in the ammonia loading graph?
Yeah, I'm looking at the graph. 1 second. The temperature does affect the graph. If you see the lowest temperature is 7 to 10 degrees on the graph, yellow cross, they are farther away from the graph. And 15 to 18 degrees around the same range, but the highest temperatures are usually closer to the line, red line. But once the loading rate is above 1, they don't seem to have a relationship. At lower loading rates, they have a closer relationship. The temperature is a bigger factor. The higher loading rates, they operate it like a roughing reactor. So at that roughing reactor stage, the temperature doesn't have much of an impact.
All right. Well, we have run over time, and there are still just a huge number of questions left. A lot of them are very good questions, but our speakers will have a chance to answer those questions offline. So I think we'll have to call this a conclusion today. On behalf of Industrial Water World and Pinwell, I would like to thank today's speakers for today's presentation, and especially thank our host, HeadWorks Bio. I thought it was a very informative and well-attended presentation. For those of you who wish to receive a certificate of attendance, please stay online. An information screen will appear shortly and with details on how to get your certificate. This presentation will be archived within 24 hours and will be available for viewing on demand from the homepage at waterworld.com. A reminder email message for the archive will be sent to registrants, complete with a direct link to the archive. Thank you again for your time today, and for our speakers, thank you and goodbye.